Hello seniors, today we're going to see the last topic for the whole IB program, which is antiderivative, also known as integration. So today we're going to see antiderivative and indefinite integral. The objectives for today's class are to define indefinite integration as antidifferentiation and calculate the indefinite integral of x to the power of n. Okay, so to begin with this concept, I told you before that integration, which is a synonym of antiderivative, as this name suggests, is the opposite of differentiating, right? As you know, the opposite of multiplication is division, the opposite of addition is subtraction, and using the same concept of opposites, we can define the integral of a number or of an expression as the opposite of a derivative, okay? The integral of an expression is the opposite of the derivative of an expression, okay? So let's see how this works. Let's start by doing this challenge. It says, what is f of x if f prime of x is 2x plus 3? So now we're trying to think the other way around from what we were thinking previously, right? Normally we would have f of x and we would find f prime of x by applying any of the derivative rules, right? But what will happen if I have the opposite situation? I have f prime of x and now I want to find the original function f of x. Try to think what the original function should be in order to obtain this expression as the derivative, okay? If you think this for a second, you can, for example, try, right? We could say that f of x, if we need to obtain 2x, maybe the original function must have here x squared, right? Because if we differentiate 2x squared, we're going to take down the 2 and we're going to get 2x, right? 2x to the power of 1. So maybe the original function has x squared, and if we have 3 here, maybe the original function should have 3x, right? If we differentiate 3x, then we would get 3 as a result, right? So this is a possible solution to the original function, and this would be the integral of this expression over here. Now, my question is this the only solution? So is it the only solution? What do you think about this? Try to think about this for a second. Is this the only solution? And the answer is no. We may find another function which has this expression as its derivative. For example, if we find the derivative of x squared plus 3x and let's say plus 2, for example, you see that if I differentiate this, I'm still going to get this expression over here because the derivative of a number is always 0, right? So this is another a possible solution, right? So that means that I can have infinite possible solutions, right? Because if I change this number, I can pick any number I want, and the derivative will always be this expression over here. So we could write the original function in a general form by saying that it will be x squared plus 3x plus c. We're going to use plus c here, where c is any constant number, right? So this is the general solution. The general solution. And c is any constant number. Okay, so with this challenge, you can already have a grasp of what antiderivatives or integrals is about, right? It's doing the opposite of what we were doing up to now by doing derivatives, right? So let's read the following. It says, we know we can find the velocity of a moving object by taking the derivative of the displacement function. This is something that we have seen, right? Velocity is the derivative of the displacement function. And write this as, okay, that's fine. Carrying out differentiation on the displacement function. Now, consider the reverse process. Can you find the displacement function for a moving object if you know the velocity function? And the answer is yes, we can apply anti-differentiation or integral in order to find the displacement function in this case. So it says, suppose the velocity function is given by vt equals 2t plus 1. We need to find a function s of t such that its derivative is 2t plus 1, right? So working backwards, we find one possible displacement function, which could be s of t equals t squared plus t. Since the derivative of t squared plus t, if we find the derivative of this expression, we're going to get 2t plus 1, right? So that's exactly the velocity function we had before, this one over here. So why do we say that s of t equals t squared plus t is one possible displacement function? So basically we're analyzing the same thing we did here. It says, the function s of t equals t squared plus t is called an antiderivative of vt equals 2t plus 1. The process of finding an antiderivative is called integration. In this chapter, you will learn about the process of integration and how integration can be used to solve problems involving motion on a line, area, and volume. These are very important applications of integrals. If you remember from derivatives, one of the most important applications of derivatives is optimization, right? In the case of integrals, one of the most important applications of integrals in real life scenarios are to find areas of irregular shapes or volume of irregular shapes. Okay, we're going to be seeing more about that. Okay, so if you take a look at this, here we have an example, right? A clear example of how this works. If we have a function which is t squared plus t, if we differentiate this, we're going to get 2t plus 1, right? And if we integrate this expression, we're going to get t squared plus t. So basically, differentiating, finding the derivative is like decomposing the function, right? Or making it 1 degree less, while integration does the opposite. It builds the original function or the function which is 1 degree above of this one over here. Okay, so that's the difference between integration and differentiation. Okay, then it says antiderivatives and the indefinite integral. Suppose that the derivative of a function f is given by 2x plus 3. Working backwards, we find that f may be the function f of x equals x squared plus 3x, right? If I find the derivative of this, we're going to get 2x plus 3, which is exactly this expression over here. Since the derivative of x squared plus 3 is 2x plus 3. Of x, yes, that's fine. But there are other functions that have the same derivative, such as f of x equals x squared plus 3x plus 1, or maybe f of x equals x squared plus 3x minus 6, since the derivative of these functions are both 2x plus 3. Why? Because the derivative of a constant number is 0, okay? Then it says the functions f of x equals x squared plus 3x, f of x equals x squared plus 3x plus 1, and x squared plus 3x minus 6 are called the antiderivatives of 2x plus 3. Any function of the form f of x equals x squared plus 3x plus c, where c is any arbitrary constant, is an antiderivative of 2x plus 3. So here you can see that, right? All of these functions have the same antiderivative, which is 2x plus 3. So it says a function f is called an antiderivative of f if f prime of x is equal to f of x. Okay, so that's the definition of antiderivative. Then it says the antiderivatives of x to the power of n are given by, and here we have the general formula to find the antiderivative of any number, right? As we have the rule for the derivatives, the power rule, we also have this integration rule, which is also available in the formula booklet, right? Where c is any arbitrary constant and n is different from -1. So you see that, and we're going to see this in the following examples here, but whenever we're integrating, we always need to add this plus c at the end in order to have a complete answer. If you don't write the plus c, then the answer would be incomplete. So then it says here, just as the process of finding the derivative is called differentiation, the process of finding the antiderivative is called antidifferentiation, or also known as integrating, okay? So let's see these examples right here. it says, find the antiderivative of each function. So we're going to work with the first one, part A. To find the antiderivative of a function, here we still do not have the symbology for that, but I'm gonna show you already what's the symbol for integrals. If we want to find the antiderivative or integral of this expression, the symbol we use in math is this one over here. This symbol means the integral, and then we write of this function, and we always write it at the end the differential of the variable we are integrating. In this case, we're integrating with respect to x, so we write dx, okay? And how do we find this? Well, we need to follow the rule. The rule says that I need to, in this case, increase the exponent by 1, which is the opposite of what we did before, which was decrease the exponent by 1. And then I need to divide that new exponent to the whole expression, right? Opposite to the derivative where we multiplied the exponent down here. Now we're dividing our new exponent and we are increasing the exponent by 1. Okay, so that's the rule for integrating. So if we want to integrate this expression, x to the power of 10, this would be x to the power of 10 plus 1 divided by 10 plus 1. So the integral, and always remember we need to write plus c, right? If you don't write the plus c, then you're going to get a wrong answer. So this is the same as saying x to the power of 11, sorry, I forgot something here. This is divided by 10 plus 1. So x to the power of 11 divided by 11 plus c. And this is the antiderivative of this expression over here, okay? So I'm going to give you a tip here. If you want to check your result, you can always, let me write that down. You can always check your result by differentiating the answer we obtain. The answer. There you go. So if we try to find the derivative of this, we're gonna see that, for example, let me write this down with a different color. If I define a function f of x, which is equal to x to the power of 11 over 11 plus c, make this a little bit smaller. There. So let me bring this here. So if we copy the function f of x equals x to the power of 11 over 11 plus c, and we find the derivative of this function, what are we going to get as a result? Let's see. If I find f prime of x, we already know the rule for differentiating. We take the exponent down and we multiply it. So 11 times x to the power of 10, the exponent decreases by 1. This is being divided by this 11 over here. And then the derivative of c is always 0, right? So I'm going to put plus 0. So I see that we can simplify 11 with 11. And what do we get as a result? We're going to get that f prime of x is equal to x to the power of 10. And that's exactly our original function we had here, right? X to the power of 10. That means that we did this antidifferentiation correctly, right? This is correct. So that's one way you can always check your result. Now let's see exercise B. Exercise B, we want to find the antiderivative of that expression. So I'm going to write the integral of, and instead of writing 1 over x to the power of 5, I can already write x to the power of negative 5, right? I can rewrite the expression and write dx at the end because we're integrating with respect to x. So we follow the same rule. We're going to increase the exponent by 1. So this would be x to the power of negative 4, right? Negative 5 plus 1 is negative 4. And I need to divide my expression by the same new exponent, which is negative 4, right? And this is plus c. And that's it. So the answer for this antiderivative would be minus 1 over 4 x to the power of 4 if I take all of this expression down again to make the exponent positive. And I'm forgetting, we always need to write plus c. Okay, so this would be the antiderivative of this expression for part B. If you want, you can try on your own finding the derivative of this, and you should get as a result this expression over here. Okay, now let's see part C, the last one. We want to find the antiderivative of the square root of, the fourth root of x cubed, right? In order to do this, it's better if we rewrite this using a fractional exponent, right? This is the same as saying the integral of x to the power of 4/3. Remember, it's always, not 4/3, 3/4, 3/4. Remember, it's always this power divided by this power. So this is times the x here. So if we find by using the same rule, we're doing the same thing. We're increasing this fractional exponent by 1, and then we divide the whole thing by our new exponent. So if we calculate 3/4 plus 1, let me do that here, x to the power of 3/4 plus 1 divided by 3/4 plus 1, right? That's what the rule is saying here. And plus c, don't forget about the plus c. So this would be equal to x to the power of 7/4 divided by 7/4. 7/4. And if we rewrite plus c, right? I'm forgetting about the plus c. So if we rewrite all of this expression in a more elegant way, let me see if I can make it fit here. I'll move this a little bit there. So if we want to present this in a more elegant way, this is the same as saying 4 times the fourth root of x to the power of 7. All of this is being divided by 7, and then the plus c at the end. Don't forget about the plus c. So here, plus c. And this would be the answer. Maybe I can take all of this down. That's better. So this would be the answer for the antiderivative of this expression over here. Okay, so I think I'm gonna stay here. We're gonna see later on in future live sessions some properties for integrals, but for now, by understanding the concept of antidifferentiation and how to do some basic example of this, we're fine. Okay, so I hope this was clear, people. If not, please let me know. We're gonna clear doubts in future live sessions. Thank you for your attention, and see you.